January the 14th, 2005. The day had finally arrived, the day that I'd thought about every day for 17 years. 1.5 billion miles away, out there near Saturn, there was something that we'd built, and it was hurtling through space at 20,000 miles an hour. Would it do just what we designed it to do, or would it all be wasted?
We went into the science room that morning knowing that whatever was going to happen was going to happen. I mean, this was the day.
There was an enormous air of expectation.
Basically, everyone I met was as excited, but also as nervous as I was about the whole mission.
Frankly, I think we were all petrified. But the very worst thing that shouldn't have happened, happened.
And it turned out that there was a major problem.
I just wanted to go away and cry in a corner.
That really ramped up the nerves. You know, there's a missing command, what else is wrong?
I really had visions now of the last 17 years having been wasted.
Watch the sky, the planets are jumping and I'll tell you why.
Growing up in the late 50s, all I knew about space travel was probably from reading about Dan Dare, for example, in the Eagle comic. I knew very little about the planets, probably from school books. All we knew was from often rather blurry, indistinct images from telescopes on the ground. I think I knew that Saturn was a large ball of gas, you know, we call it a gas giant, and that it was about 1 billion miles away from us here on the Earth. But I certainly didn't know anything about Titan. I didn't know that it was one of Saturn's moons orbiting around it. I mean, you have to remember, we didn't have any spacecraft images, of course. And then something happened to change all of that.
Half an hour ago, the Russians announced that they'd put the first man into space.
It's the voice in space of Major Yuri Gagarin.
Not only one of the greatest scientific events, but one of the greatest occasions in the history of man.
It was absolutely mind-boggling, and it's impossible now, really, to imagine the impact that it made.
Man in space to be shown.
Excuse me, what do you think of the news?
I think it's fantastic.
Well, I can tell you he's now back, safe and sound.
Really? I didn't think he would get back.
Well, I say it's the very best for his good luck to the chap myself.
Within months of Gagarin's flight, he embarked on a world tour. And I think it's true that the first port of call was the United Kingdom and London.
Major Gagarin, could you tell us what you think of the reception of the British public?
Прием английским народом везде очень теплый, очень хороший, дружеский прием.
The welcome I have been given by the British public has been overwhelming. It has been most friendly and kind.
Везде открытые улыбки, теплые сердца.
I see smiling faces everywhere, evidencing very warm hearts.
What about you? Would you like to be a spaceman?
Oh, well, it all depends. If it comes up like everybody is a kind of craze, I think I might have a go.
You might have a go, might you?
Yeah.
What did you think of the Major?
Oh, I liked his uniform, and I liked the company all around him.
The school that I was at, Highgate, was very close to Highgate Cemetery. Of course, every visiting Russian dignitary had to visit the tomb of Karl Marx. I remember school was cancelled for the afternoon. It was such a big event, you know, Gagarin coming to London, coming to Highgate. I think I only decided to come along here at the last minute. I'm not sure why, I don't know that I'm a believer in fate, but it must have been fate, mustn't it? And it was my eureka moment, seeing that man standing here, small man. But the thought he had been in space for what was it, 96 minutes, the first astronaut. And I was hooked from that moment on. The Gagarin flight was really what kick-started it all. It really took us out of that science fiction era into the era of practicality. And one can see it as the first step on our exploration of the solar system with humans and also with robotic spacecraft.
Oh, it's one of those things, if you grew up in the late 60s, early 70s, you know, space was everywhere, it was the most exciting thing, you just wanted to be involved in it. Probably couldn't even imagine that you would be.
There was a little bit of affluence, and some of the social boundaries and barriers were breaking down. You know, there was the so-called youth revolution, and I was caught up in many of the demonstrations that were going on against the Vietnam War. It was a fascinating time.
It's one small step for man, one giant leap for mankind.
I was always interested in space. I was interested in unmanned space exploration, you know, seeing other planets up close.
All of this helped to cement, I think, this hope, this dream that I had, that I could actually take this further. I could get my physics degree, I could then perhaps do a PhD and really move to be a part of this whole worldwide space activity.
Don't move it till I see it. I stirred it up with my feet. Hey, it is! I can see it from here. It's orange.
Only once every 175 years are the major planets, Jupiter, Saturn, Uranus, and Neptune, so aligned that a spacecraft can visit all four on a single flight. The rare opportunity to probe these planets occurs in this decade, the 1970s, and will not recur until the middle of the 22nd century.
Most of what we knew about Titan, at least at this time, was from the Voyager spacecraft. We knew that Titan was about 5,000 kilometers in diameter, so bigger than the planet Mercury. It had a thick atmosphere. This is what really made it stand out amongst all of the planetary satellites in the solar system. It's the only one that does. But we knew essentially nothing about the surface, because Titan is permanently shrouded in orange haze or smog, which meant that none of the images showed anything of the surface. We know it's very cold. Saturn and its satellites are so far from the sun. The atmosphere is very complex. It was known to have at least 12 different gases and probably having some similarity to Earth's very primitive atmosphere, one that we lost probably billions of years ago.
There was organic chemistry on Titan, which was interesting, but Titan wasn't warm enough to have liquid water, which of course is one of the sort of prerequisites for life as we know it. And I think Titan sort of faded into the background in a sense for much of the following decade.
Well, towards the end of the 1970s, jobs in British universities were very difficult to come by. And I saw an advertisement, which was very hard to resist, to go and work on a project called Giotto. Now, Giotto was Europe's Halley's Comet mission. And the job was at the University of Kent to be project manager for the DUST instrument. I applied and I got it. So at the end of 1981, we moved to Canterbury on a 2-year contract, I ended up staying there 18 years. Giotto flew 594 kilometres from the nucleus of Halley's Comet. I mean, remarkably close. And we detected about 30,000 dust particles. You know, these are the particles that make up the tail of a comet. I think it was the mission that gave Europe confidence that it could really do ambitious things in space. After the success of Giotto, the European Space Agency were very democratic about selecting the next scientific mission. They had 5 candidate missions. And we got involved in a team on a mission called Vesta. Now, Vesta was going to fly past an asteroid, and we were part of the group that was looking at the possibility of firing some penetrators. They would be fired into the surface of the asteroid and make measurements of the physical properties. And we came to the day of selection, and to our horror, it wasn't Vesta that they chose. They selected a mission called Cassini, going to a place called Titan, a place that I'd hardly heard of, and we were completely deflated and dejected by this. I remember still the journey back to Canterbury from Bruges. We went on the train and the ferry, and it was a pretty depressing, glum journey. We got back to the lab, and I said, look, have we really wasted the last year? Is it possible that some of the work that we've done on the Vesta mission, which they didn't choose, we could actually adapt to this strange place, Titan, that they were proposing to go to? We sat down with a cup of coffee and had a look at what it was that the European Space Agency had chosen. Cassini, as proposed, was going to be the most ambitious space mission ever sent to the outer solar system. It was planned to carry the first dedicated set of instruments for Saturn and its system, and it was to carry a probe that would detach and land on the surface of Titan. Now, pretty soon, we realized that the part of it that really interested us was the probe, which was going to descend through Titan's atmosphere. It was going to make the bulk of its measurements during the descent. And we realized, of course, how embarrassing it would be if the thing landed and it didn't have anything with which to make measurements on the surface. So we literally listed all of the physical properties that you might want to measure on the surface of Titan. We then wrote a proposal in response to the call for proposals to produce a quite ambitious, though small, little instrument called the Surface Science Package. We beat the deadline by about a day. We sat and waited for the decision. And to our amazement, we were selected.
A new and very exciting space probe is being planned for the 1990s. Dr. John Zarnecki is closely associated with this probe, and we are delighted to welcome him down to the Sky at Night for the first time, but I certainly hope not the last. Welcome, John.
Thank you. I do my Sky at Night programme. I'm going to do a programme about Titan. Who to invite on it? Obviously, John. I didn't know then what a good broadcaster he was. Now he came, and we discussed Titan.
But of course, so far, we've only been able to study the top part of it. We still don't know what the surface is like, and that's the reason for sending up this Titan lander. Will you tell us about that, John?
I should tell you that it's already been christened, in fact. It's called the Huygens probe, named after the Dutch physicist Christian Huygens, who discovered Titan. I was billed as a Titan expert. I hadn't written a single scientific paper about Titan, and this was a very bizarre situation.
He didn't know much about the surface of Titan, but neither did anybody else, and he knew as much as anybody.
All in all, this is one of the most ambitious vehicles ever planned. What do you think of the chances of success?
We must be optimistic. You would never embark on a mission like this if one wasn't optimistic, and I expect that we might be sitting here in 13 years' time discussing the results from the Cassini mission. I think it began to dawn on us just, in the weeks after we were selected. We had to produce an instrument, one of a set of 6 scientific instruments, a bit bigger than a shoebox. It had to travel in a probe in deep space for over 7 years, descend through this thick, rather mysterious atmosphere, and then make measurements on this very alien and unknown surface. And it had to give us answers. It had to make sense of this alien world. I mean, that was a daunting prospect. I had to start building up the team, and there are several critical positions. Arguably, the most important position is the project manager. That's the person who really runs the show day to day and brings the whole thing together. Okay, one thing we've got to decide is exactly who to send to the meeting with ESA.
One of my colleagues knew John Zarnecki from maybe 10, 15 years earlier, and he said, I saw John the other day and he's looking for a project manager, why don't you give him a ring? And amazingly, because of him, I had this new space science career. The instrument had originally been selected in 1990, but the team were just getting going in 1992 when I arrived. They just really had a few prototypes on the bench. Some of them were very Blue Peter. I remember a washing up bottle with a steel ruler attached that was the density sensor, and the thing was huge, and we had to turn this into an 8-gram sensor to fly to Titan.
Well, when Mark came on board, there were 2 big issues that we had to face. One was to put the final team together, and more importantly was to get the funding, because being selected was only half of the battle. We then had to get funding from our national agencies. Our funding situation is stable. If you call underfunding a good thing to report, we were underfunded 2 years ago, and we're underfunded to the same extent now. We were cut back to about 2/3 of what we actually needed to do the job. So we had to look at clever ways of getting around the funding shortfall. This was around the time of perestroika, when the Iron Curtain was coming down.
Bulldozers tonight began to open new holes in the Berlin Wall. Throughout the day, thousands of people have been crossing freely from east to west of Berlin and back again.
And I saw an opportunity here to use some of the professional connections that I had with Poland to see whether we could go there and use their desire to work with the West in scientific research. And we found out that they were quite experienced at building space instruments. So basically we cut a deal. They would build a part of the instrument in exchange for coming on board and seeing essentially how space research was done in Western Europe. Now that was one thing that we did. The other was to take advantage of the fact that we were a university. And one thing that universities have generally in profusion is students. And generally students are fairly cheap. I won't quite say slave labour, but nearly.
The whole project seemed a lot like science fiction in the sense that somehow we were going to build this thing that was going to travel 1 billion miles through space and then parachute down through this atmosphere at minus 200 Celsius and touch the surface of one of the moons of Saturn. I mean, it just sort of boggles the mind that you can contemplate doing that.
Ralph is enthusiastic about everything he turns his attention to, and he became very quickly embroiled in all aspects of Titan, and one of the tasks that we assigned to him was to develop the penetrometer.
Well, one of the things we really want to answer with the surface science package is what is the actual nature of the surface of Titan? What's it made of? Is it solid like ice, or is it slushy, or is it liquid? And this part of the package, called a penetrometer, aims to do that by measuring how hard we land in it as the probe comes down. We measure the impact forces.
It's very strange. You sort of come into this from the outside thinking that there's some massive team of top-notch engineers and scientists who've done this all before, and that you'll be allocated some little part of it. And the reality is there's never enough people, and everyone's sort of improvising because nobody's built anything that went to Titan before. So it was at first a little strange and surprising that I'd get to do this, but it was an incredible opportunity.
In the early days of the project, we were being followed by a BBC crew who were filming some aspects of the project for an Open University programme.
It was an eye-opener. It was the first time I'd been involved in that kind of thing.
They actually set up a sort of little video diary for us, a little passport photo booth where you just sit in front of this video camera and say what had happened.
It's April the 13th. Last week we donned these crazy suits and went in the clean room to assemble the engineering model Penetrator.
This instrument will perform thermal properties measurements to show the thermal conductivity and the temperature of the Titan Ocean.
This will be sent away to be shaken, baked and electrically tested in what is called the top hat. That is the thing that holds all the experiments. As you can see, it's quite small and fiddly, but I'm rather pleased with it.
Science students tend to be nerdy, and I think as a group we conform to that stereotype. But it means you're really utterly focused on what you're doing. I mean, you have sort of 3 years where you have no other commitments other than to do your research. And because building a space experiment, going to Titan, is such a motivating thing, it was really, really wonderful actually to have that focus.
The penetrometer was a fairly simple sensor in concept, but actually doing it well took a lot of work and a lot of effort. Ralph was involved with running loads of prototype tests and dropping things into buckets of sand and seeing how different tips, shapes responded, etc.
I remember one of the first things we did was got some sand from Whitstable Beach, and that was a huge mistake because it was real sand at the sea, and so it was all wet and salty, and of course salty water is an electrical conductor, and of course the signals we got from that were just terrible.
It was building an instrument to go somewhere that we didn't know what we were going to land on, and that was a real part of the fascination.
It's one thing to make a measurement in the laboratory, it's another to make an experiment that is going to work for sure 7 years later, after traveling through space for 1 billion miles, that's going to work at 200 degrees below zero, and that isn't going to suffer any kind of problem.
The biggest fears we had were landing on absolutely sharp exposed ice, which meant for us the probe might die pretty quickly, and our challenge was to get the data back before the probe died.
At the time, one of the main speculations about Titan's surface was that it was covered by a global ocean of liquid methane. And so I spent quite a lot of time doing my PhD modeling the splashdown dynamics, looking at all the old Apollo literature of how a capsule decelerates when it hits the water, and trying to figure out how much the Huygens probe would decelerate if it landed in liquid methane.
A lot of it was theoretical stuff. Do we have global oceans? Do we have seas? Do we have lakes? Anywhere in between.
The natural sort of speculation was, well, that it'll be like landing on Mars or landing on the moon. But we have no idea what the materials really are. If it's ice, or if it's like sort of ground up ice like sand, or if it's some sort of organic dust that's just very fluffy. So we had to sort of consider all these possibilities. We certainly didn't know anything that would let us exclude any of them.
This is the final engineering model of the Huygens Surface Science package, containing its 9 different sensors. We've got here the speed of sound instrument to measure the speed of sound in the atmosphere and on the surface. Here we have the sonar, designed to send a signal down to the surface of Titan or to the bottom of the lake to measure its depth. Inside this enclosure here, we've got 6 further instruments to measure various properties of the liquid or the solid surface. And finally, we have here the penetrometer.
Yep,
output lines are clear, and we're running at about 6 psi over ambient.
Once you get into the hardware phase of the project, there's testing, and some of these tests run for tens of hours at a time. There were times when I felt that I knew my milkman better than my family because I was arriving home at 5 o'clock in the morning.
Okay, can we have temperatures please, James?
Top cavity 111, bottom cavity 114.
For this particular mission, one of the really unusual things was when we got there, we were going into a very, very cold environment. So many of the sensors we needed to test in liquid methane. It is a little bit hazardous, so we were doing this on the roof of the physics building. I guess the logic being that if we blew up, we only blew ourselves up and no one else.
A project like this inevitably puts strains on all the individuals involved, and that's challenging enough. I'm not sure that my family really understood quite what I was doing. They sort of supported me, but probably thought that I was, the crazy scientist, and maybe every family had to have one crazy scientist.
I was very lucky in the sense that I'm quite a sort of self-motivated, self-driven kind of guy, so I didn't need a lot of hand-holding. And that was just as well because John was a busy man. The job he was doing as a university lecturer and building this space experiment, is quite demanding. And he was going through some personal difficulties at the time too.
The early days of the project coincided with, the breakdown of my marriage. So I have to say that there was about a year in the project that was very, very difficult. I mean, I find it difficult even to think back to those times. It was difficult to keep everything going, frankly. And I was very lucky. I had a really good team who, when things got very difficult for me, they were more than able to keep the show on the road.
There were some very, very long working hours involved, particularly when you get to the flight model and you're trying to get everything to meet the deadline. If you miss the delivery, you're not going to Titan.
You ever have one of those weeks where nothing works? Our fax machine is broken, the photocopier didn't work, the coffee machine is broken down, even the BBC's bloody light has stopped, so we have to improvise with this desk lamp.
I'm sitting in this dark old laboratory with an experiment that's not working, and you sort of think, is this really what I want to do? Have I made the right decision? But then you sort of remember the bigger picture.
The project developed. It was hard and painful at times, but finally we got to the very last test. This was the vibration test. And can you believe what happened? The damn thing broke. The structure which held our instrument together cracked.
I was personally devastated to hear the news. I realised the impact of it straight away, that even just rebuilding the top hat was going to be a problem, but the fact we had to rebuild sensors too meant that every aspect of the project had its hands full with a huge workload. There was really the possibility that the European Space Agency might say, I'm sorry guys, you're not going to make the delivery date, you're not going to be on the probe, you're not going to Titan. And at that point it was at least 4 years of my life dedicated to that instrument. We had to find a solution, we had to get out of this hole. It had taken maybe 6 months to build this flight model, and we were 2 weeks away from delivery and had to rebuild the whole thing. For John it was an even longer time on this project, and again he knew instantly that there was a chance we were getting thrown off this mission.
We came up with a strategy whereby we would deliver the engineering model to the spacecraft. That would enable ESA to continue with their program. They couldn't hold it up.
This meant we had to dismantle the whole thing, remove all the harness, fix the structure, but also build flight spare instruments, calibrate them, put the whole thing back together. In the end, it took about 3 or 4 months to go through the whole thing again, but it was touch and go.
We worked around it, we came up with an alternative design, and we delivered that to the spacecraft. Late, but it was working.
Titan, the hazy moon around Saturn. Today, a huge rocket is being prepared to explore that distant world. Europe and America have joined forces in a $3.5 billion mission called Cassini.
This was it. We flew out to Florida for the launch. To our surprise, we were actually greeted there by protesters.
With legions of protesters climbing the gates at the air station, opponents have maintained that NASA's plutonium-powered satellite could kill the innocent should something go wrong.
They blow up all the time here, you know, and for some reason of insanity that I can't imagine, they're going to stick 72 pounds of plutonium atop this thing.
What I want to see is a safe world. I don't want nuclear in space.
If you go out to the distance of Saturn from the sun, sunlight is very weak. So you can't use the traditional way of generating electricity on a spacecraft, which is to use solar cells. So you have to do something else, and this is true of all outer solar system missions. And what is done is to use radioactive material, in this case plutonium, and you use the radiation that it emits to essentially to generate electricity. That's the only way you can do it.
It just seemed to be this sort of knee-jerk reaction that radioactivity is this terrible thing, but for me it was just a necessary part of the spacecraft. But how would the protests affect the launch? Would they get in the way? Would we be getting tomatoes thrown at us?
I mean, it took me back to my time as a student in the 1960s, when I was doing the protesting, when I was carrying the banners. Now there I was having to cross the picket lines.
The launch was in the middle of the night at about 3 o'clock in the morning, and I think because of the security and so on, they had special buses arranged for us.
You nervous?
Yes, I am.
Yeah, I'm a little nervous. Yeah, just a bit. I mean, 7 years' work, and this is the make or break night. I mean, there's a lot of work down the line from here, but this is really where one place where it could fall down.
It was always in the back of our mind that any rocket is only 95, 97% reliable. So there's a good chance that if the mission fails, it was going to fail now.
LC RCO-2, recorders are running.
Launch command systems now enabled.
T-minus 1 minute, 30 seconds.
Sat there biting fingernails and trying not to get too nervous, waiting for the okay that they are going to launch.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
I saw flames at the base of the rocket, and the first thing that went through my mind was that the rocket's caught fire and it's about to blow up or something, because the ignition happens, but it's several miles away, and so the sound of the ignition hasn't reached you yet. You just see the flames, and then you see the rocket start to ascend. And then the direct sound hits you, and there's this sort of wall of deep rumbling bass, and you get the sense, wow, now we're really on our way.
Cassini goes up, and it was almost by design. There was a cloud about, I think, 1,000 feet or so, right above the launcher. And then after a few seconds, it went into this cloud.
There was almost an explosion of light. It looked like the thing had blown up. This cloud was just a huge ball of fire, it looked like.
For a fraction of a second, it was horror. It's gone, we've lost it. But then we saw Cassini appearing above the cloud. It was coming through, and then it went up into this clear black sky, absolutely serene, truly wonderful sight.
Once it was off and through that cloud, you knew it was going. You knew it was going to be a good launch. I guess I kept an eye on the rocket all the way up till it was a tiny dot.
During the journey to Titan, we actually moved our team to the Open University in Milton Keynes. A lot of things do happen in some respects. I mean, one is rather sad because the team that we'd built up to design, build and launch the SSP, much of that team dissolves. We don't have the funding to keep that team going all the way through. But we kept a core team together because roughly every 6 months we switched the instruments on and we ran through what are called housekeeping tests.
How did you go into Mo4, on time or on altitude?
This time we went in using the 7 kilometers altitude.
Okay. We'd check out the instruments, make sure the spacecraft was working fine, that our instrument was working fine. There were a few minor things we monitored and a few software bits we changed. Nothing too major from our side.
What you have to understand is that when Huygens was planned to be descending onto the surface of Titan, it will be relaying its data not directly back to Earth, there just wasn't the power for that, but sending the data up to Cassini, which would be flying some thousands of kilometers overhead. Cassini would then relay it a few hours later back to the Earth.
There was a major scare on the spacecraft. They tried a particular test of the communication system and realised that there was a problem, and with the mission as it was designed we weren't going to get the science data back.
One thing that was tried was using a radio telescope on the ground to sort of pretend to be Huygens and transmit a signal as if it was Huygens to check that Cassini could receive that signal correctly. And when the results of that test were reported to us in a science meeting, they sort of said, yeah, that we did the test, and we were not sure quite what happened because we didn't get all of the data back.
To put it simply, it's as if Huygens was transmitting on Radio 1 and Cassini was receiving on Radio 2. In other words, there was a very slight mismatch in the frequencies, but it was enough to potentially scupper the whole of the Huygens project.
That was obviously a huge problem, very frightening from the scientist's point of view, but the system quickly got together, came up with some options for solutions.
There were 11 possible options that were found that might be able to address this problem. In the end, we picked on one of them as being the potential saviour. This involved Cassini, instead of releasing Huygens on the first orbit around Saturn, releasing it on the third orbit. That would change the geometry between Cassini and Huygens by just the right amount to bring the two frequencies back into synchronism. Quite remarkable.
Now, how long does it take a spacecraft to travel 2 billion miles between planet Earth and Saturn? Nearly 7 years is the answer. And tonight, for the spacecraft Cassini, the journey is nearly over.
Well, today's the culmination of our 7-year trip through space, and we're arriving at Saturn, and we're going to fire the engine to stop us into orbit around Saturn. So it's the end of the trip, but really the start of the tour. The excitement for me is in the future when we get close to Titan, but this is a big moment. It's a kind of a bit of a party atmosphere here in Pasadena to sort of celebrate the arrival. There have been 1 or 2 occasions in planetary exploration where spacecraft have blown up on arrival, when they've used their engines for the first time.
Current Cassini altitude 20,700 kilometers, 12,900 miles, with a speed of 30.7 kilometers per second, 68,600 miles per hour. We are slowing down.
Cassini would have to use its main engine for a very large burn to break into orbit around Saturn. So it was a tense moment. We'd be crossing the ring plane as well, which has some element of hazard to it.
Flight, SWATCOM.
Go ahead, SWATCOM.
The Doppler has flattened out.
Okay, we have burn complete here for the SOI orbit insertion burn.
That was a big moment. And then once it was in orbit, then sort of everything was just kind of quiet and basically following the script, just the way it was supposed to. It would actually be a little over 6 months before Huygens was delivered to Titan.
Outside is frightful, but the fire is so delightful. And since we've no place to go, let it snow, let it snow, let it snow.
Christmas Day 2004. It was the day of the planned release of the Huygens probe from Cassini.
Basically, there were a set of explosive bolts that released Huygens, and a set of springs pushed it off on spiral rails that gave it a spin to stabilize it.
Everything was pre-programmed on Cassini. We were monitoring it, and it went fantastically. From that point on, Huygens was on its own, completely autonomous. It didn't even carry a radio receiver. So from then on, if we'd wanted to change something, we couldn't. We were completely powerless. The die was cast from that point.
When I got into the control centre, basically everyone I met was as excited but also as nervous as I was about the whole mission.
There was an enormous air of expectation. It had been building up for the last few days.
We went into the science room that morning knowing that whatever was going to happen was going to happen. I mean, this was the day.
Some people had said, oh, nobody will be interested in this. But by this time, we had something like 300 of the world's press there waiting to see what would happen.
There was lots of vans and TV cameras parked outside, and anyone who could be grabbed by a media guy was getting grabbed.
There's a little bit of a siege mentality. A scientist was kind of walled away in our little room.
It was hard to concentrate on the important work and not get distracted by all the calls for your time.
I couldn't stop thinking that about 1.5 billion miles away, out there was something that I had built, about this size, and it was hurtling through space, about 20,000 miles an hour, and it was about to get a rude awakening. The plan was Huygens would hit the top of Titan's atmosphere at a speed of 7 kilometers a second. Over the next 2 minutes, it would slow down to about 400 meters a second. At that point, Huygens would deploy the first of 3 parachutes, and that would enable it to float down to the surface at a relatively slow speed. Then the 6 scientific instruments would be switched on to really perform their job that they'd been waiting for about 7.5 years. Around 10:30 in the morning, a rumour comes through that one of the largest radio telescopes on the Earth has picked up a signal directly from Huygens.
It looks like we heard the baby crying. We still can't understand what it tells us, but clearly it tells us that the probe is alive. The entry has been successful. We are on the parachute, and the probe is transmitting.
Project scientist Jean-Pierre Le Breton announced that news, and there was a huge cheer, and it really meant a lot to all of us. We knew that the most critical part of the mission was successful.
This is absolutely fantastic news. It's like hearing the ringing tone on the phone. It tells us the phone is working. There's no information on it yet, but it's absolutely fantastic.
That was great news because it means that it wasn't gone without trace, that even if we didn't get all the data back or if the probe didn't make it down to the surface, at least there was something.
We have a signal, meaning that we know that Huygens is alive, so the dream is alive.
Though it really encouraged us, we still had a long time to wait. The real scientific data wasn't expected till halfway through the afternoon.
All positions on the Peterloo. I'd like to let you know that in about 4 minutes we will receive probe telemetry from Huygens.
We were expecting to get the data at around 1725 Central European time. So we were gathered in the main control room. There was lots of banter, lots of discussion. People were excited, people were talking. As we got towards the time, we were watching the screens, I noticed that things were starting to get a bit tense.
The Rusa is still not powered, and we wonder what was the plan to power it on.
I was just listening to some of the discussions on the voice link, and there was something that concerned me. There was a missing command, and I knew that for some instruments this was going to be a technical problem. We're maybe going to have some system problems and lose some data. So that really ramped up the nerves. After we've had a really good news, or we know the probe itself's worked, have we lost the data?
1725 came and went. Nothing. Absolutely nothing on the screens. I can remember the mouth going very dry, and it got very quiet in that room.
And okay, maybe I've got the time slightly wrong. Is my watch exactly right? And for the first minute it wasn't too much of a concern, and then you could feel the tension in the room building.
I really had visions now of the last 17 years having been wasted. Something had happened to our probe. Parachutes hadn't deployed, the probe had burnt up, the transmitter had malfunctioned. I really imagined us staring at blank screens. And then, and I think it was about 6 minutes later than we expected, suddenly there was a shout, and I looked up and I could see on the screen in front of me one of the columns where we were expecting data was full. This was real data coming through from Huygens.
It was absolute huge relief to see the screens light up with colour and display. You could just feel the tension pop in the room.
people could start seeing from the data various aspects of the descent. They could tell what speed we were falling at. After a while, somebody said, you know, we've had 2 hours of descent. I mean, we must be getting close to the surface. My instrument, the Surface Science package, its main aim was to make measurements for however long we lasted on the surface. We were told, initially anyway, to plan for 3 minutes on the surface only. So we designed it for all of our measurements to be done in that very narrow time frame.
If we didn't reach the surface by 151 minutes, then actually we time out into surface mode, which would be disaster because we'd actually lose some of our major data. And the probe was descending way, way slower than anyone expected.
SSP, Kevin, status report.
OMSSP, status is nominal on B.
All stations, big, we have touched that.
We think we detected surfing.
And in the end, we had just over 3 minutes to spare when we hit the surface.
I came back into the support area and heard that the data had been delivered. And so I went up to my colleagues and I wanted the data. You know, it was on a stick, so I was like, who's got the stick? Give me the stick.
I ran into the lab. The guys were there clustered around one single PC screen, and just as I got there and I was about to ask the question, do we have data yet, the screen burst into life and we saw every single sensor had worked. We'd got effectively a perfect data set, and the boys were ecstatic.
There was tremendous outpouring of emotion in that room, and I have to say that I did go off at one point into the corner, and I was crying, frankly. It was, I think, the release of all that emotion after all of those years. We'd been through so much together.
So we are the first visitors of Titan, and the scientific data that we are collecting now shall unveil the secrets.
A few of the guys were looking just at the impact data and looking at the penetrator data, and there was a distinct spike right at the start of the signal.
We've hit something hard. It's as if we've hit a crust on the top, and then after that the material below is much softer, and we pushed into that without much resistance.
We had to make a chart for John to present to the media at the press conference later that evening of what the possibilities were, and we sort of wrote, well, could be sort of like packed snow or maybe sort of wet clay, but there's this extra spike at the beginning, so maybe there's a crust.
One of my team actually has suggested an alternative analogue, and this is because of the crust perhaps we see there, and that is creme brulee. But I don't suppose that will be appearing in our papers.
And the media just loved that. That was, in the headline in Nature magazine that week. You know, Titan team gets its just desserts with creme brulee surface or something. So that was really good PR coming up with that analogy.
We can report that the Surface Science package collected data for 3 hours and 37 minutes. Apart from any scientific and engineering importance of that figure, some of you might have heard that we had a sweepstake in our team for the moment of impact, and I'm slightly embarrassed to have to tell you that it was I who won the sweepstake. And the prize, which was a very old bottle of Scottish medicine, was consumed by the team at about 2:30 this morning.
John put in a good bet. He was 10 seconds off on a 2.5-hour descent time. That's almost a magical touch, I think.
Oh no, it seemed actually entirely appropriate. I mean, you know, he was the leader. He was the guy that made it all happen.
There was barely a single day since the project had started when I hadn't tried to imagine what the surface of Titan looked like. I remember the first few images that we saw were quite remarkable. We saw this landscape carved with what looked like river channels.
The theory that there had been liquid on the surface of Titan was true. It was absolutely amazing to see it, the first people to see that image. Also, it struck me that it looks so much like Earth.
You know, it looked like Arizona, it looked like the French Riviera, it looked familiar, and that wasn't something I think we were expecting.
And then we saw the landing image, the area immediately around the probe. It was an area that seemed to be strewn with boulders, and I just couldn't believe that our probe, that we of course knew so well, and my beloved instruments on board it, were actually sitting quietly, serenely on this surface environment. What we've learned is that Titan's surface is incredibly varied. It shows features which show some similarity, at least superficially, with Earth. We're now pretty certain that we see lakes and seas of liquid methane. There's a whole range of geophysical processes going on that's shaping the surface of Titan. We've learnt an enormous amount about the atmosphere. We have a stratosphere, we have a troposphere, we have weather. We have weather on Titan. I think it shows our sphere of influence, if you like, our sphere of knowledge, expanding beyond the Earth. Our machines have put their foot on the surface of Titan. We've shown that we can do it. It's part of that process of exploration that I think we've always done. It's part of what defines us as human beings.
To get closer to the mission to Titan and explore the stars yourself with the Open University's virtual planisphere, go to bbc.co.uk/Titan and follow the links to the Open University.
Stay with us, Maggie and Chris, on A Martian Mystery, The Sky at Night, next on BBC4. Then a Ken Loach classic, the film that made his name, his 1966 masterpiece, Cathy, Come Home in Half an Hour.